morning. I would like to thank the organizers for giving me this opportunity to talk today. This is work done in collaboration with Luca Gamberale, and it's about collective oscillations of protons in hydrogen-loaded metals. Of the two, I would say I am the newcomer to the field. And as a newcomer, what I see, I can say it is a large body of experimental evidence. In the field of low energy nuclear reactions. And also we can see in the last few years there is an increasing number of publications in mainstream journals. We can say it is not anymore an isolated community. There are institutional research programs and private companies with commercial claims. Maybe efficiency is still a problem for commercial applications. So these are my impressions. I just put here a few titles of papers from scientific reports we had from Professor Wang. So it is published in Nature Scientific Reports, although some of the reactions reported in the paper already look very unorthodox, to say the least, like this one with a neutrino incoming in the reaction, or this one with a fusion of two oxygens. And then we have more papers in scientific reports by Fomichet Samilov, an Indian team. We have the papers in the Japanese Journal of Applied Physics, the impressive paper by Professor Tsersky in Physical Review C, big review by Melzina and collaborators. So it is becoming a mainstream field of research. There is a persisting clash of opinions inside the community. There is a persistent reputation threat and accusations of poor science from the outside. Also, of course, competition with conventional fusion fiction is not so welcome. In some sense, there are too many theories. There are internal opposing camps among theorists. So there are still problems. Our proposal is not a final theory. It fits in the general heterogeneous situation where two physicists, and Luca Gamberale has a long specific experience. He's a former student and collaborator of Giuliano Preparata. I am new to this field, but I have quite a long experience of study of new claims, like, for example, claims of gravity superconductor interactions, both in academia and private labs. Now, the process we are considering is electron capture in condensed matter. We know this was previously studied by Guido and Larsen. This is the reaction, one proton plus one electron giving neutron plus a neutrino. But of course, you need, there is missing energy on the left. So the question is, where does the energy come from? Guido and Larsen proposed the idea that the effective mass of the electron in this reaction is much larger. So the so-called hypothesis of the heavy electron. This is hard to prove theoretically and hard to believe in the theoretical physics community for many reasons that I cannot explain right now. Then the idea is that the neutrons which are generated cause transmutations of heavy elements, but also reactions like hydrogen plus neutron giving deuterium, or deuterium plus neutron giving the tritium. And then, of course, there is still to be explained why no gamma are produced, and if it is possible in this way to produce the helium-4, and so probably not. So our idea is that the missing energy in the electron capture reaction in condensed matter comes from the energy of coherent protons. So not from the electron, but from the proton. This is definitely more similar to the process of electron capture in a nucleus, because in the nucleus, the energetic balance of the reaction can be fixed by the proton in one step, in one shot, because the proton has strong interactions, nuclear interactions with the rest of the nucleus. So it has an energy spectrum with large gaps of mass. On the other hand, condensed matter systems normally have incoherent interactions, and the energy gaps are very small. So there is the energy in condensed matter, but it is too fractionated. The problem of fractionation of a large quantum of energy has been studied from Einstein and collaborators since 2008, exactly with applications to fusion, to cold fusion, and he considered fractionation of the fusion energy into phonons, in a process also called down conversion. And before I go to the detail of the coherent oscillations of the protons, I mentioned that there is a full calculation of the E3 process by Luca Camperale previous to our work. This calculation assumes coherence, so it does not contain a proof of the coherence, but includes very important points like the rate equation relating the pumping energy to the final energy output, which is quite important point for the efficiency of the reaction. So in our calculation, in which we prove the condensation of protons into a coherent state, we consider a metal in which hydrogen has been loaded, and the protons of hydrogen go to some specific points in the lattice called tetrahedral sites, and they are bound there by a sort of by a potential which is almost exactly an harmonical potential. So there will be some frequency of oscillation omega. In addition to this, a plasma frequency, because it's a system also with electrons, plasma oscillations, and the plasma frequency is called omega p, and there will be the possibility of generating cavity photons, because, as I will explain better, we are in a finite volume, in a sort of natural cavity, so we will have also photons. We have computed the one particle energy spectrum of the protons bound to the lattice in this way, and it turns out to be like this, with 12 bound states and then continuum of other states. And the eigenfunctions of the protons are very much localized, much more than for the electrons, of course, very much localized close to these tetrahedral sites. And this localization justifies an approximation of the protons as bosons, because there is practically no superposition of the wave functions. And clearly, all this can be applied also to deuterons, and in that case, it is exact, because they are bosons. So how do, in our opinion, the coherent electron capture works? In the first stage, we imagine to have n incoherent host protons in their ground states in the metal. N is very large, of course, not here in the picture, but you must imagine it is about at least 10 to the 9 in a grain of metal. And you see the small energy levels of the single oscillators. Now, our proof, which is quite general, not just related to to the nuclear applications shows that that can be, in certain conditions, a condensation to a coherent state. The coherent state has a lower ground state. Okay, this is like a phase transition to a state with a lower energy. And the gaps, the energy gaps in this coherent state are much larger. So in the second phase, we imagine to give some external energy, a pumping process to this coherent state. So we have the excitation of coherent state. This is a representation of the excited coherent state. In the coherent state, all the protons behave in the same way. So they go to the excited level. Then we can have electron capture because there is enough energy to generate the neutron and the neutrino. And then, of course, the number of protons diminishes by 1, and they all go to the ground state. And then what happens? Of course, a neutron can cause a nuclear transmutation, and in the last phase, the gamma generated in the nuclear transmutation can be reabsorbed by the system, so with a non-radiative relaxation. Because of these large gaps, they can absorb the gamma. So I will show you briefly also some part of the equations. So this is the part of the Hamiltonian concerning protons. Here you can see the two references of the publications. The plasma oscillations have the effect to renormalize the original oscillation frequency of the electrons to a new to a value that we call omega prime. Then we have the Hamiltonian of the photons. This is a very important part. The calculation, in some sense, must convince, if we want to collaborate with them, we must convince quantum optics people, so the quantum optics community. So we must be very careful about the treatment of photons. We start with photons of frequency omega, and we introduce the matter field interaction in the standard way. And then there are two crucial mathematical transformations to be done with the photon field, preserving the commutation rules, in order to eliminate the diamagnetic term. This is a standard transformation, this one. It's a linear transformation, which normally in quantum optics makes sense if you have a cavity. In our case, the omega is not the omega defined by the artificial cavity, but it is the omega of the oscillators bound to the lattice. But in any case, it is very sharply defined. That's the important point. Then another technical but very important point is that we are considering the cavity with modes oscillating in all three directions. So we have a 3D improvement factor, which is essential to increase the coupling between field and matter and cause the condensation. As I said, the finite volume acts as a natural cavity. The reason is that there is inside 1 micrograin of the metal, there is a different relation between the frequency and the momentum of the photon compared to the external. So there is a mismatch which prevents photons to escape from the material. There can be possible losses, and we took them into account, not in the analytical model, but in numerical calculations, and we saw that condensation is not affected by these possible losses. In the end, the effective Hamiltonian looks like this, where we can see we have 3 multi-photon modes with frequency omega prime and off-shell momentum, which causes the confinement. And here is the expression for the energy gap per particle of the coherent state. This gap can become negative, and then we can have the condensation. Now I would like to briefly mention some work in progress, which is about a numerical computation of excited states, so not just the ground state of the coherent quantum oscillators. This is a simplified computation because we consider oscillators with only two states that we call qubits, harmonic qubits, because they have two states but an harmonic dynamical Hamiltonian. And so in this work, we are studying the energy transfer between two external oscillators mediated by these coherent qubits. And we find that the excitation transfer as independence of the frequency is very different in the coherent phase and in the uncoherent phase. In the coherent phase, the excitation transfer has only one peak centered above the base frequency. In the condensed state, so when the coupling is large enough to cause condensation of all protons in one single state, we will have excitation transfer also for higher frequency, which is exactly what we want in order to have these large gaps in the system. So, in conclusion, our calculations and numerical simulation show the formation of coherent state of protons in hydrogen-loaded metals with a cubic crystal lattice. We have seen that in these states, protons oscillate in phase frequencies of the order of 10 to the 15 hertz, and importantly, with a fixed phase relation with the electric field. This electric field is self-generated. It is trapped in the material, especially if the material is made of micropowders. The energy gap is of the order of 1 electron volt per particle, so this is a state which is robust against thermal fluctuations. And the next task of this model is to compute the excited states of the coherent system and to study the pumping process, which is very important for the efficiency of applications. The dynamical mechanism considered offers an alternative to the Wigom-Larsen hypothesis of the heavy electron, and it is definitely closer to current models in mainstream physics. The consequences in terms of nuclear transmutations of the neutron generation by electron capture would be similar to those which have been already studied in the literature. So the analytical calculation was done for a very large number of protons in the RWA approximations, and the numerical calculations are exact, but they are only made for a small number of particles. So this is one is going to skip. And so finally, let me just make a very short advertisement for the journal Symmetry, of which I am an editor. The editor-in-chief is Professor Olitsov, and we are running a special issue about quantum synchronization of oscillators and qubits. So thank you very much for your attention.
Any questions? Okay, thank you very much for your nice talk. I have two questions for you. First one, so maybe the comments is better. This if you are speaking about condensation of the protons and large energy gap. The problem is, of course, that protons have a half spin, and they cannot be treated as bosons. The neutrons, of course, you can do it, but if you study, these levels, I think there's not allowed to do it. And therefore your calculations can be maybe much easier applied, for neutrons. This is one point. Another point is that this kind of energy levels for hydrogen could be observed experimentally, very easily, by solid-state physicists. We know that plasmons, there are proton plasmons, of course, in the metallic lattice, which are known. They are connected to electron plasmons as well. The energy of them is much lower. So I think the energy spectrum you have calculated could be measured probably experimentally, very easy. So the question is, you have maybe something, some data, experimental data from other groups that you can compare. And the third point is, if you produce neutrons, it's not enough to produce fission, because you have thermal neutrons, and thermal neutrons cannot produce fission. If you, of course, for uranium or very heavy nuclei, it is possible, but for iron or nickel or something like this, you need additionally 40, 50 megaelectron volts to produce fission and transportation. Okay, this 3 points. Okay.
Yes, thank you very much. Yes, concerning the possible experimental observation of the levels, this is a very good suggestion, and we have to look at it. For the first point, I said the wave functions of the protons are very much localized, so we can take into account the fermionic effect, but it looks like it can be very
because
small.
Yeah, you have completely different situation. You can there is not compensate, no. So
Yes, of course.
There's a problem, and then you have a problem with the temperature, because of course you can go down to temperature 0, and then you have no decoherence. And there's a question: what is the lifetime of this kind of thing compared to the kinetic energy in the lattice? This is a very important thing. Of course, it can happen theoretically, what you presented, but
Now, if you look at the wave functions, you can see they are very much localized. And then the third point about neutrons. Yes, of course, it is possible that the neutrons generated are of higher energy, depending on the initial conditions. Especially if the pumping is very quick, we have calculations. If the pumping is very quick, you can generate neutrons with high energy. Anyway, so this is all these consequences are very wide-ranging. We have not yet analyzed them.
Okay, thank you. So, just one short question. Okay, I have a quick comment. I would suggest to consider applying your calculations for coherent electron states, which it is known, for example, from superconductor research that electron coherence is observed up to 100 Kelvin, whereas nuclear coherence is only observed up to 2 Kelvin in superfluid helium. So there is at least 2 orders of difference. The lighter particle can get easier into coherent state. And regarding the exclusion principle and statistics, I have been studying with my co-author, Giorgio Vassallo, the clarification about electron statistics, and it was actually in Scientific Journal published our article on electron statistics that I think would be useful for your research. So I encourage to apply this approach to electron coherent states that could maybe have something to do with the alien.
Yes, thank you very much.
Okay, let's have speaker again.